Welcome to SICE Petro's presentation today. We're going to cover petrophysics inversion for CO2 sequestering. We've got some examples. I'm Mike Uland. We're going to have on today's outline, we're going to have a few slides for carbon sequestering, just so we're all on the same page. And we're going to talk a little bit about, aquifer. First example, aquifer storage or sequestering. They tend to call that CCS. And if you're using CO2 for enhanced oil recovery, they tend to call that CCUS. We'll talk a little more about that later. The important point is to store CO2 or sequester it and get your credits. There's a lot of permitting requirements. We're going to talk about a tiny bit of those. CARB, Government 45Q, EPA class CO2 injector permits. They all have about the same requirements, similar. And one of the things that there is that you have to provide petrophysics constraints that are going into your geomodels. And your geomodels are going to feed flow sim models. Turns out flow sim models are required to get your permit. So you're going to need a geomodel, and you're going to need lots of kinds of constraints, including petrophysics models. In these three examples, we're going to use SICE Petro's petrophysics inversion software, iMineralysis. Way more information than I can even handle. There's hundreds of pages of this stuff. But if you cut out bits and pieces of it and start looking at it, this happens to be for the California CARB board. Different sections, they're going to require what they call CO2 capacity, storage capacity. You and I would think of that as oil field reservoir pore volume. But irregardless, you're going to need porosity, heights, net pays, water saturations. And we're going to need some top seal lithologies and geomechanical properties, petrophysics data to support that. We're going to need well logging plans that we're going to show how we're going to get the data from. And you're going to need baseline data for future measurements because they do require that you monitor the injection in the future. Lots of detail, but stuff we're going to need. All right, this is a busy slide, but it basically breaks down on the left aquifer or this CCS storage versus EOR, where you're producing a little oil with the CO2 and you're going to trap that CO2 in the reservoir and sequester it permanently. They call that CCUS. Basically, for the aquifer, our first example, we're going to inject CO2 in a saline. They need to be saline aquifers. And of course, they're going to migrate up dip. Hopefully there's a closure or a pinch out. They have to be below the liquid CO2 pressure depth. You don't let this get to gas. You keep it as a critical liquid. And you can do multiple zones as long as you have monitoring and other requirements. On the right, this actually happens today, a good bit. There's a few of the aquifer examples on the left. CO2, particularly in the Permian, you're capturing it from plants or natural sources, but only plants like ethanol or fertilizer plants count. It has to be a natural source, not coming out of the ground in the Four Corners area. You're going to take that CO2 and you're going to inject it, and it's going to be miscible, and you're going to sweep extra oil over. You're going to separate the CO2 that's produced with it. You're going to cram it right, compress it, and put it right back in the ground. And when you're all done, you're going to shut this in. And the same requirements. You're going to have good top seal to make an economic project. For aquifers, you need good top seals, need good pore volumes. Now, it works the same way. This happens to be a BEG slide, but it works the same way as an oil field. We know the area that the CO2 plume will stay stored under. We think we do. Flow sim models are going to help tell us that that's true. But from petrophysics, what I need is net pay and total porosity. Actually, what you really need is effective porosity. We're going to need some fluid properties, and we're going to need some other things from our petrophysics, water saturations, etc. But the formulas work the same. What you're really up to is what I would call pore volume, or they call CO2 storage capacity. So, first example, we're going to do an aquifer storage. There's never been any oil. So they would call this carbon capture and storage, CCS. And we're going to take a look at the storage zone and the cap rock, and we're going to have some choices here. So the first thing we're going to do is set up an iMineralysis model. You've seen this earlier or maybe later with the SICE Petro group. Just matrix inversion of your minerals and your input logs. But some extra constraints, they're going to do thousands of iterations here. It's why I like this. It's not just a deterministic model. So in the end, we're going to optimize on that. Just a standard red-blue input curve matches. What I'm really interested in is the minerals and the fluids. And in this case, this would be the storage zone. It's a saltwater filled sandstone. It's got a salt, and sometimes this is going to change to anhydrite and shale. We're going to find out. It's got some trash rock, maybe a monitoring zone or two, and it's got freshwater aquifer. So this is not oil and water. This is freshwater with some salt water being all salt water. So this is our freshwater sandstones that we're going to have to protect. So we are going to have a monitoring zone, and we're going to have top seals. Now you can do this conventionally. So this just happens to be gamma ray, resistivity, neutron density, which is the input data we're going to use. And you're going to QC that data. And you could go right to a conventional or a deterministic inversion, one case or try out a few cases, or conventional, find a porosity, find a V shale, find a Phi E, find an SW. And you could get there. But with the inversion models, I can try out lots of cases. And when I have to go to peer review for these permits, it's sometimes easier to explain an inversion model and that you tried 1,000 cases and here's what's optimum or appears to be optimum, rather than justify every little piece of a conventional model. Either way, you start with the same data. Either way, you can get to the same answer. So what I've done here is it's the same input data on the right for each wells track, but I've added the lithology tracks and the fluids tracks. And you can see that in the top seal, my salt in purple is going to tend to disappear, and I'm going to go to a shale or shales with anhydrites. So I do still have a top seal on this right-hand side, and I definitely have better pore volume, but I still have adequate pore volume, and I have a monitoring zone in this area A. In all cases, I have an aquifer, freshwater aquifer, that I'm going to have to protect. So besides feeding my geomodels, you can use this for quick look screening and other kinds of things. So in this case, I've taken area A and area B that was on the right-hand side of that cross section, and I've taken the top seal and I've crunched down the percentages of the seal minerals. So a couple of evaporites, basically think salt and anhydrite, and I'm losing those as I come down into the B area, replaced by shales and some salts, stringers, and a little more anhydrite. I can crunch down the reservoir properties for where we're going to be storing it. They are a sandstone in that interval. In fact, it's pure sandstone in the best of the storage intervals, but it's got a lot of shale interbedded with it lower in the section. And you can see the cyan porosity is going to increase in area B. So how would you use this in a screening model? You'd simply say, oh, good. I've got a lot more pore volume down in here. We're going to set our project up down in this area. But remember, I don't have a monitoring zone here, and my seal is adequate, but maybe I have a better seal. So one of the things to think about is, should I take the monitoring zone, where I have a good monitoring zone and slightly better seal, and I still have adequate pore volume for the CO2 that I want to sequester. So you can use this for early screening before you have to do all the flow sim models, which is what this was used for. Next example for how we're going to use this, and again, we're going to use iMineralysis for, excuse me, for looking at the petrophysics inversions. Here, we're looking at an EOR project, and they need to know about top seal containment and really what percentages of the salts and hydrides do they really have here. Quite literally, they got a little salt above in shale, but quite literally, we're going to set the model up, and here we're going to set a couple of petrophysics models up. I'm going to set one for the seals. In fact, I'm going to set a couple above that for different types of seals. This one's for the first or secondary anhydrite seal. And then we're going to set models up for the storage zone and the primary seal, which is shale. And here, this is a known oil field. They've been producing oil out of the main zone. There's traces of oil in what I would call a monitoring zone. The seal may be held, maybe this is actually got a second hydrocarbon water contact if it's really there. And you've got great anhydrite seals, and you got better shale and other seals way above that. So seal here is probably not the problem, kind of thing. So we're going to do the same thing. I'm going to set up the input data, gamma ray resistivities, neutron density. Here we have a PE. And I put in the operator's track for their estimate of what porosity might be when they were doing their initial CO2 capacity screening and beginning to set their permits up. We do have this additional seal that's an anhydrite up here. We're going to go ahead and use iMineralysis, and we're going to do the inversions. So I'm going to add on the inversion tracks. So lithologies and fluids. Yes, it's a shale, but it's not quite as good a seal as you think. And maybe that's why we had a little hydrocarbon leak up. So even though we call it a secondary seal, this is probably going to be the top seal. And even though they're going to use this as their monitoring zone, this may well become CO2 storage. Primary CO2 storage will initially go in and try to recover extra enhanced oil out of this zone. It is a four-way closure for this structure. It's a carbonate structure. Last example. Same kind of thing. We're going to use a carbonate to store CO2 in the primary zone. But here our secondary zone is not above us, it's below us. And it was an oil field at one time. It's a residual zone. You see these in the Permian and other places. So a bit of tutorial before we go there for anybody who doesn't know what a residual oil zone is. Basically, you had a paleo oil water contact and everything was full of nice black oil. And at some point, it's not that the seal leaked, it's that the whole thing tilted, basin wide almost. And different fields have different residual oil zones, these ROZs. But what happens in these is in your conventional oil field that's produced today, you have capillary pressure and you have an oil water contact. But that's not really true because I had a paleo oil water contact with cap pressures that's no longer there. But I have this residual oil zone, 20, 30, sometimes 40% oil stuck on the rock for a million years. And so you get these really strange cap pressure and other kinds of things you have to put into the model. So if I drill a well, I'm going to make clean oil day one right here, just 20, 30 foot above the contact. 20, 30, 40 foot below this residual contact, even though I've got all this residual oil, I'll make a 1% oil cut. So conventional wells were always produced here. But if I'm going to store CO2 for EOR, CO2 works just as good scraping that 30 or 40% residual oil off, and it gives you a bigger pore volume. So we're going to look at how would we do that. So again, I'm going to set up iMineralysis inversion models. In this case, I'm going to set up vertically, like before, a top seal model. Actually, I've got another one above that that has salt in it. This one has just anhydrite and some silts. But in my main pay zones and the residual zone, I really don't have much silt and I have very little anhydrite. So I've compressed that model down a little. I've dropped a few pieces. Gives me a better match to the hydrocarbon that was in the main zone and the residual zone hydrocarbon. That's why I did that. We'll move on here. This is the same kind of thing. It's the input data that I'm QCing. So gamma ray, resistivities, neutron densities, and we were lucky here we had don't have that much in the Permian, but we had PE curves in the outside track 4. And here we have a couple of seals. Actually, I've got a third seal that's really, really good above this. So seal is not the problem here. The question is what does the main pay zone look like that they're storing, running the EOR project in and storing CO2? Turns out you actually store about 95, sometimes higher percentages of the CO2 used because you're capturing it and putting it right back in. And you can do the same thing with the residual zone, and we're going to see that's a significant pore volume. The rock quality is actually going to get better as we go deeper. So same kind of thing. We run the inversion models, and here I ran several inversion models. I ran model 1, model 2, model 3. I didn't like model 3. I liked model 1's anhydrite seal better, but I liked model 2's match to the saturations in the main zone and the saturations in the residual zone going into the aquifer. So we did do a little mixing and matching here. The other thing is that where sometimes I run these individually and tune them, but when I want to make big changes across the field, iMineralysis has the capability of running all wells at once with the same starting model, but tuning it to each well's individual results. And that's the way this was sort of run. Okay, let's go on and take a look at what we have. So what I did is I took the top seal and again crunched that down to a bubble map. And we always have the anhydrite seal, but we do have places that have a little more dolomite and the anhydrite maybe is a little thinner. All of these are good seals because, like I said, seal 3 that I'm not showing above this is even better. So seal is not the problem. What I want to show here is the lithology is not that much different in the main pay zone to the upside CO2 zone, this residual oil zone where we could store additional CO2 and recover additional oil to pay for that cost. And if we go to the fluids that are in those zones, what we see is on the left, and remember these wells are drilled from 85 to 2010, or at least they're in this plot. So some of the early wells have better water saturations. By the time they produced for 30 years and started CO2 in the main pay zone, you're going to have a lot less average oil saturation. But as you come up on the ROZ, remember I'd make 100% water or 99% water cut, and I have a slightly decreasing oil saturation until I get down to true aquifer. Different wells do look different. That's a thing to map and think about in the ROZ and what happened in that paleo zone. But the point is we've got a lot more water and only residual oils in the residual oil or the ROZ. Same kind of thing. Just going to take the top seal and I'm going to look at the average pH over that, or the porosities. Those anhydrites are really tight. There are a few little streaks that have some porosity in the dolomite there, but it's a couple percent. The rest of that is 0. Our main pay zone, the crest has the best rock and the best pH. It's highest on structure. But if we'll start putting CO2 in the residual zone and start collecting that oil, we can double our pore volume to store what they would call CO2 capacity. So for the same facilities, pipelines, I get incremental oil to help pay for it, and I can double the storage volume. That's pretty cost effective. So sometimes you want to look at these residual zones in the Permian. Okay, that's pretty much it for today. Doesn't matter whether I'm building geomodels or whether I'm doing flow sim. I'm an engineer, but I really do like petrophysics. I think it's important calibration point. All models are plausible, and you can use them to constrain anything. But don't believe they're 100% right. They're all wrong. They're just useful. And what we use these iMineralysis inversion models for, besides the geomodeling constraints? We used them for the freshwater aquifers, for the monitoring zones, for the cap rock, and the main CO2 storage intervals. And thanks for your attention. If you got questions, get a hold of us at Sice Petro, and special thanks to Rinaldo, Kevin, and Patricia, who made this presentation possible.